Okay, hello everyone, Assalamu alaikum. So this is one of our videos of the ML Summer School, Bangladesh. So this is basically the first expert talk, which is going to be an academia talk. And we have Raima Islam Apu here with us. She is currently doing her master's from Harvard University. So okay, without any ado, let's add Raima Islam Apu to the stage. Hello, Assalamu alaikum Apu. I believe you can hear me.
Yes, Mithul, I can hear you.
Okay. Thank you so much for accepting our invitation. Would you like to introduce yourself first?
Yes, for sure, I would love to. But before that, I would like to thank Mithul for arranging the summer school. I
Mhm.
know, especially in Bangladesh, kids and students and even professionals, we don't really get I would say, the opportunities to learn from experts or even attend sessions like this, which gives you like a end-to-end view of how ML works, what is important, the math, the code, the
Mhm.
algorithms behind it that makes ML today, and also given the rapid pace of how ML is being developed every single day. So thank you so much, Mithul, for arranging this. Now, a little bit about myself. My name is Raima, and I am currently doing my master's in computational science and engineering at Harvard University. And I'm also a data science intern at Solid Biosciences, which is a biotech company. And I am utilizing LLMs and agentic AIs to automate some of their workflow process. So I have also created a slide which is
Okay.
about me.
I'll just add it to the stream, Apu. Okay, you can just continue.
So a little bit about me. I also did my undergrad from Bangladesh, from Brack University, same university as Mithul. That's how we got to know about each other, and I studied in computer science. Currently, I am doing my thesis, basically my master's thesis with Harvard T.H. Chan School of Public Health, where I'm working with the biostatistics department on using explainability and deep learning techniques to detect cancer cells. And before I started my master's, I was a research intern in machine learning at Hanyang University, where I published over 10 papers in the domains of natural language processing, computer vision, human-computer interaction, and bioinformatics. And the papers I published were all in the top tier conferences and journals such as Nature, ICLR, Chi, Wisdom, CSCW, ACCV, etc. I also have various hobbies, but I wanted to keep it like very concise. And some of my favorite things to do when I have free time is definitely cooking, exercising, and nowadays, watching. I think this is a problem among Gen Z and even millennials or boomers, where we spend a lot of our time watching brain rot content on Instagram, Facebook, or TikTok. So that is something I also kind of enjoy doing. So moving on. Um, we will be talking about three papers today.
Mhm.
One is in computer vision, one is in, well, LLMs. What are some of the recent findings of their strengths and weaknesses? And the last one is it is also a paper by Apple. It is a bit different. It is a bit different from like the usual papers we look into when we are talking about LLMs. So let's get started. Now I would like to introduce SAM2, which basically means segment anything in images and videos, which is the next evolution of promptable segmentation that works, let's say, seamlessly on both images and videos. So, what is SAM2 and how does it work? So, imagine when you click on an object in a photo, what SAM2 will do, it will immediately return like a precise, let's say, a mask around that particular object. So when I say mask, it will create like, I would say, a shadow or like a detection kind of bubble around the area that you click on, so that that particular area is identified. Now we imagine we extend that to into a video where with a single click, SAM2 not only segments the object in the current frame, but also it let's say propagates or like continues to detect that particular um, shape or mask throughout all the subsequent or like the next upcoming frames. So it creates like a masklet, so which tracks the object over time. So you can refine the result at any point by simply clicking again. So at its core, SAM2 is like a streamlined transformer architecture. So if you have been dabbling with LLMs or even not LLMs, if you have been dabbling with natural language processing or even like computer vision, you must have come across the transformer architecture, which is an encoder decoder architecture, which actually revolutionized the scene of machine learning, which and transformer also serves as like the base model for LLMs. So thank you for transformers, which made our lives a lot easier. So since it's like a streamlined transformer architecture, it is kind of like a higher vision transformer image encoder, which extracts um, let's say various features or multi-scale features once per frame. And it also has a memory it also has like a memory attention module, which attends to like the recent frames and earlier prompts like simultaneously, and basically like a cross attention kind of mechanism going on, which retains all the context, so that even if like an object disappears or it is like kind of disappearing from the frame, a late frame click can recover it. And it also has a lightweight mask decoder, which predicts multiple candidate masks to resolve the ambiguities and also tell you if the object is hidden behind something. So these design choices and the architectural choices makes SAM to not only like 6 times faster than the original SAM on images, but also capable of real-time video segmentation at 30 to 44 frames per second. To train SAM2, the team at Meta built like a three-phase data engine with human in the loop annotation. And it is very important, especially when you're working with like AI models, to not fully like rely on like the model doing every single thing for you. There has to be like human intervention to assess whether the results that we are supposed to get, or especially like the data set that we are working with, is it appropriate to our use cases or the type of work we want to accomplish. So not to make the LLMs or the AI models do everything by themselves, but bring in like humans to in each of the processes to kind of check and verify and validate whether it's working properly or not. And it achieved and this achieved an 8.4 times speed up in the masklet creation. um, and this resulted in the SAV dataset where over 50,000 videos and 35.5 million masks dataset has been created, which is 53 times larger than any prior video dataset. So training proceeds from image pre-training through joint image and video batches to a long context fine-tune, and it follows a very strict curriculum. that scales properly or effectively with time. So we have been like talking about like the architectural choices and the technical requirements for creating SAM2, but why do we even need to know about this? Because when you are working with interactive video segmentation, SAM2 hits the target accuracy with 3 times fewer clicks than the prior combinations of the previous SAM. Plus, if you have any standalone trackers, that also works very good with SAM2. And in the classical semi-supervised VOS setting, where you get like a mask on frame 1, SAM2 sets like a state-of-the-art score which outperforms specialized trackers even when they use perfect masks. Um, on single image benchmarks, it edges out the original SAM while running at 130 frames per second. So with even if we are not talking from like the numerical metric angle, uh, if I were to talk about like the achievements of SAM2 in general, it does um, it did create like a promptable visual segmentation, which unifies videos and images. So it's like it's not like you can only use it on images, you can use it on videos as well, and it works well on both. And a single transformer with a streaming memory handles the reappearances and the occlusions, and a massive diverse video data set has been open sourced to the community. So if you have ideas of your own, you can definitely use like the SAV data set, which Metafair made it open to use for all. And yep, if you search on GitHub, the code, the checkpoints, the data sets, and interactive demo, everything has been released. And there are edge cases where like short changes, very thin or fast objects, and multi-object efficiencies, they might not give like the best results yet. But SAM2's prompt anywhere design allows you or any users to recover from errors with minimal clicks. So that was about SAM2. Now moving on. To this paper. And just for context, these papers, especially the first one and the second one, they were published this year in ICLR. So it's one of the major AI conferences out there. So if you have like a paper published in ICLR, I, as an AI researcher, especially today, you kind of made it in life because getting accepted here is quite difficult. So these two papers were some of like the spotlight, or I would say the papers which gained a lot of attention. Yeah. So now moving on to this paper, transformers learn low sensitivity functions, investigations and implications. Um, we in this slide, especially, we ask why do transformers outperform other models in both accuracy and robustness? So the authors here actually introduce token-wise sensitivity, which is measuring how often the model's outputs flip when we slightly perturb a single input token, thinking of adding a bit of noise to one word in a sentence or a patch in an image. So let's say in the infinite width limit, self attention learns to prioritize low frequency Fourier components. So, in simple terms, transformers are biased towards simple functions that barely change, when you nudge one piece of the input. So, as a toy experiment, even in, let's say, one layer attention model trained on synthetic data, when two equally predictive solutions exist, the model picks the one with lower sensitivity, even if that means leaning on more frequent tokens rather than the rarer ones. Um, in vision and language tests, on datasets like CFAR10 and ImageNet 1K, vision transformers match CNN's accuracy but register 10 to almost 100 times lower sensitivity, and they hardly budge when you tweak a single patch. When we are talking about language tasks on MRPC and QQP benchmarks, um, Roberta models show sensitivity at around 0.03 compared to 0.09 for LSTMs. Moreover, LSTMs are more sensitive to the last few words, whereas transformers spread their attention and sensitivity evenly across the whole sequence. So these kind of if you look at the overall picture or the overarching um, objective and the overarching characteristic of transformers, we see that they prefer sturdy functions, which do not flip their prediction even if you slightly corrupt one input token. So they basically want to see that if we because when we are working with, let's say, Kaggle datasets or I don't know, these curated datasets from Meta, Google, Microsoft, and whatnot, or any sort of like big research labs, these are very cleaned data sets, very ideal data sets, whereas in real life, that's like far, far from the reality. Especially because, like, let's say in my internship, I get like so much unstructured data that most of my time goes on to just cleaning the data and preparing the data. Even my friend who is doing an internship at Amazon, she told me that 90% of her time went away just parsing the data. So yeah, that's why it's very important to see that when you're dealing with real life scenarios, how are these models working? Are they working as efficiently as they do when they're working with clean data sets? Um, Now, we want to see why low sensitivity bias matters. It gives us better robustness, where lower sensitivity tightly correlates with higher accuracy under corruptions. Let's say on CFAR 10C dataset, vision transformers beat CNNs on noise, blur, weather, and digital distortions. We can even train the models to be robust by adding a simple noise-based regularizer or Gaussian noise augmentation, which further slashes sensitivity and boosts the robustness. Now, it gives us a flatter minima. Models with lower sensitivity converge to flatter loss landscape basins, where the sharpness metrics drops by 4 to 5 times. The flatter minima are widely linked to better generalization. So sensitivity gives us a practical proxy to watch. For the training insights, during grokking on algorithmic tasks, sensitivity steadily falls long before test accuracy leaps. This means you can monitor sensitivity to detect hidden progress when loss curves flatten out. So, the main takeaways can be to track the sensitivity during training to spot overfitting or hidden grokking phases. We should regularize with Gaussian noise or like a mean squared error penalty on noisy inputs to push sensitivity down and the robustness up. We always have to remember that transformers succeed in part because they learn functions that barely budge when one token is nudged. Um, so that's all about this paper. Now moving on to the last paper, which I think is the most interesting one. That's why I kept it for the last, which is illusion of thinking, understanding the strengths and limitations of reasoning models via the lens of problem complexity. So this is not really like a published research paper in a conference, but this was a paper released by scientists at Apple, and it tells us how why LLMs, we sometimes, even though they are capable of doing a lot of amazing things, but especially if it is being compared to like human intelligence or how humans think, this paper actually challenges that maybe we are giving way too much credit or having way too much hopes for these LLMs to actually mimic how the human mind works, and how and why LLMs are being even represented as something that can definitely surpass um, human intelligence. So, why should we even study the thinking process in LLMs? Because if you have been dabbling with prompting techniques, you must have come across with chain of thought and reflection, which may, put LLM, let's say, benchmarking scores at like higher places, but it does mask the true reasoning behind, why the LLM gave that particular result when you asked it a question. Existing evaluation focuses on end accuracy and ignores the trace structure and the scaling behavior. So, um, so let's say over the past year, the researchers have discovered that prompting these models to explain the steps, which again, chain of thought or self reflection, it can dramatically boost the performance on like reasoning benchmarks. But there is a catch, as most studies only look at the final answer and ignore how the models arrived there. So the researchers at Apple, they wanted to know whether the shiny these, oh, our LLMs mimic like human understanding, human behavior, whether these reasoning traces actually reflect like genuine logical processes, or they're just like very cunning or clever like pattern matching. They have to kind of test this. They built like a controlled test bed of classic puzzles. Let's say Tower of Hanoi, checkers, jumping, river crossing, and blocks world, where each puzzle can be made simpler or harder by adjusting a single parameter, like the number of disks or pieces, and they ran the model step by step through every move and extract its immediate move list using a simple regular expression, and then verifying each move with a simulator. That way, they have like an exact record of what the model did and when. What they found was that reasoning models fall into three distinct regimes as the complexity increases. First, on easy models, um, sorry, first on like the easy puzzles, plain language models actually outperform the fancy reasoning models, and they're more accurate and use fewer tokens. Next, at moderate difficulty, these LRMs, the basically the reasoning models, pull ahead and they leverage their extra thought steps to get the right answer more often. But finally, as puzzles become more complex, both simple and reasoning models collapse to zero accuracy. And the reasoning models even start using fewer tokens as if they like give up thinking altogether. So if we dig deeper into the data, we can see in that paper that they plotted accuracy against the number of reasoning tokens. On medium complexity tasks, you will see that the advantage for LRMs is that they invest more tokens and get more puzzles right. Yet the investment has like diminishing returns because once the puzzle depth crosses a critical threshold, the accuracy becomes much lower and the token usage it declines. So, in simpler words, these models hit like a hard ceiling on how much reasoning they'll attempt, even if you give them more budget. They also looked at the chain of thought um, is when the chain of thought gives like the correct answer. As the puzzles get harder, the correct solutions only show up as much later in the trace. um it as in it shows up much later, and not even, and sometimes it does not even show up at all, revealing like a self-correction latency. Most striking thing is when they explicitly prompt the model with the exact algorithm for the puzzle, but it still fails after the same number of moves. So this kind of tells us that the model, uh, even if you give the model an algorithm in plain text, it isn't enough for it to reliably execute its step-by-step logic. So at the end, what does this all mean? That while these reasoning models produce convincing reasoning steps or traces, their behavior is like overwhelmingly driven by pattern matching. So it relies basically on something it has been trained on or it has like seen before, rather than actually using like logic or critical thinking like we humans do to kind of justify our opinions, thoughts, and our reasoning behind something. Uh, so it does not use like a true internal logic engine. So they cannot generalize beyond moderate complexity, and it will not push past like the internal effort limit. So breaking through that ceiling will require a lot of fundamentally new architectures or training regimes. Basically nothing short of mm, making the model learn how to even genuinely think like humans do. So, yeah, these LLMs are actually far from perfect. So I would say that as my closing remarks, don't worry too much about LLMs taking over your jobs. Yes, times are really tough right now, but if you put in the genuine effort to learn the math, the again, the reasoning, the architecture, the technical depth behind each of these models, each of these algorithms, which Mitul is already teaching in his summer school. If you put in like the genuine effort to learn data structures and algorithms and do the required lead code problems, I am confident that you will be fine, even among the tough market, and obviously network a lot with different people. So thank you so much for attending this session. And yep, I will pass the floor to Mitul if he has any closing remarks.
Uh, Apu, thank you so much, Apu. I believe we have some questions. We'll take these questions. We have, I believe, are you comfortable taking the questions, Apu?
Sure.
Okay. So just take it. Just as I believe there's basically Ahmed Ifrad. Is basically you've been talking about the papers, right? The papers published in the platform. So he's mentioned that he's currently like selecting a undergraduate thesis in computer vision, basically working for that. So he's aiming to work on a cutting edge problem that aligns with the recent global research trends and has the potential to be um, published in a top tier journal. So could you suggest some high impact and emerging research areas or topics in computer vision that would be suitable here for
Yes.
undergraduate research? Yeah.
For undergraduate thesis, I first of all, especially it seems like you wanna publish it in conferences like NeurIPS or CVPR, ICCV, etc.
Mhm.
uh it is, I don't know like which university you're currently attending, but if your university has, let's say, the capacity to work with very very large data sets, I would suggest that the data set that I have mentioned in segment the SAM2 paper, which again it is an open source data set by Meta, and also like CFAR 10, you can definitely look into those data sets and see if you can find any relevant problems from those data sets. And usually, what my approach was to kind of try to do something novel is that, especially from the architectural or the mathematical side, it is a bit unfortunate, but unless you are working with like PhD students or like already working with like very, very highly accomplished researchers, bringing novelty from like the math side or like the architectural side is quite difficult. But what I actually did, and when I was working with research, so I was working with Azmain Toshikwasi as well, who was my previous research partner at Hanyang University. We were finding out problems which are relevant to where we are from, basically Bangladesh. So whether it be in NLP, whether it be in LLMs, we would see like whether in Bangla language, what sort of work has not been done yet, which has been like widely done in English language, in Arabic language, in German language. So we would try to kind of recreate, not exactly, I would say, copy paste. That's not how research works. So we would try to bring in novelty from the topic side that, hey, this has never been done in Bengali language. We have not seen like, let's say we want to understand like the cultural nuances in LLMs, whether it is being able to capture that or not in Bengali language in the context of Bangladesh. So we would present papers on that, and that made it much the process much smoother for our papers to be accepted in these conferences. So especially from the context of Bangladesh, given that we have a huge, like, let's say traffic jam problem, or like, let's say, the roads are broken, like in every single street. So, see, from the context of Bangladesh, can you solve a problem using like the recent models? And obviously, because in the second paper, they brought in novelty just by, even though it's like it was published in ICLR, at the end of the day, if you understood the paper well, they're actually solving a big problem by making like small changes. So basically, in the input tokens, they're only changing like they're bringing in noise in one of the input tokens, and that's it. They're basically just seeing how the results are panning out. So your approach should be to start from your root level and see what sort of changes you can make. So I think if you do that, you will definitely get there by publishing in top conferences.
Okay.
Yep.
Great. So yeah, Amit also mentioned that he is from Brack University. Okay. So also another query is basically the main goal was for the folks who want to like attend this session was to know like what's happening in the US, basically talking about the research topics. So currently you are studying at Harvard. So what are you seeing the trends basically? What are the trends basically for the ML? Which kind of projects they are basically focusing on currently with the students or the academia? We know most faculties or students are currently focusing on LLM because this is how the trend goes on. But what is you saying basically? What are you seeing currently or seeing the trend in Harvard and US?
Mm, so basically, for Harvard and the US, both the three papers I presented are from the US. So I think I sort of like covered the US side already. And from Harvard's side, um, I would say in terms of AI, Harvard is not maybe one of the, let's say, the leaders when it comes to AI, but
Hmm.
definitely I would say a lot of interesting work is being done at Harvard,
Hmm.
especially what different departments are trying to do is like, be it like physics, mechanical engineering, materials engineering.
Hmm.
Everyone is trying to adopt AI into their systems, so be it like in photonics and optics, in quantum computing, or even in quantum mechanics. So I have been seeing, like, at least my friends who are in PhD programs, they are telling me what the work that is being done. And also from like the hardware side. So actually the TPU, if you have used Google Colab, the TPU
Hmm.
was actually created by a professor here at Harvard, H.T. Kang.
Hmm.
I will be taking his class next semester, and him and his PhD students are doing pretty amazing work to kind of bring in efficiency into these let's say GPUs, TPUs, CPUs, so that it does not exhaust, these LLMs do not end up exhausting all the resources. So a lot of, like, from the sustainability angle, a lot of interesting work is being done. And also from
Hmm.
like the a human computer interaction side, um, a lot of people are working on with companies with Google Meta to create like user experience and interactive designs to make, let's say, using the internet easier. So these are some interesting works I've been seeing here. Yep.
Yeah. I would, I believe, yeah, that should be enough for our audience. So if they have any questions, I would obviously request you guys kindly add it to the YouTube video or stream. This will be live, or this will be saved in our YouTube channel. So yeah, in future, I believe Ramapu can come up and answer this question. So yeah, thank you so much, Apu, for your time. So yeah, that should be it. Thank you so much.
Thank you so much, Mridul, and thank you so much for attending, everyone. See you.
Yeah, yeah, that was Ramapu. And okay, so another few things which I would like to include, that is, so Ramapu recently just mentioned like three papers, and she talked about those, like, the points, the novelty of the papers, right? So there were a few terms maybe you have come to know for the first time, but yeah, stay tuned. By the end of the whole summer school, I believe you will learn all of the topics, especially talking about data wrapping and so on. A lot of things, terms maybe that's totally new to you, but I believe that is something the video today or the session today actually will encourage you to actually stay tuned to the whole summer school, right? So yeah, okay, this was our first expert led session. The next session will be on August 15th, so that will be taken by and Microsoft MVP. Okay, so yeah, thank you so much for attending this one. So this was our first live video. So stay tuned. From the next Fridays, we will have our live videos as well as the content published as well. Okay, thank you so much. So see you soon.